So what I want to do here is talk a little bit about the differences between evoked and unevoked data. So continuous data like EEG and evoked data, and then evoked average data. So we kind of have clear in our minds, you know, what the differences are. If you remember the slide at the beginning of the electronics section, we looked at the order of magnitudes difference between like EEG and brainstem auditory potentials, you know, three to four orders of magnitude difference in signal strength. So that's kind of what we're going to get at here, are these kinds of classes of brain activity. And we're starting now to really start to think about the data as opposed to what the data represents in terms of how it's generated and the things we need to do to record the data. So we want to start to think about the data and try to understand how the data is produced. I want to make a distinction between mapping and monitoring, because we'll talk in the tumor section about a lot of mapping, which is very precise, focal, trying to delineate where pathology may be with respect to an area of the brain you want to preserve, and then monitoring where you're continuously recording, trying to feed that information back. So there's a distinction there that I'm going to try and make. And how these different classes of data fit into that. So mapping is this anatomical identification of neural structures which support specific functions. And monitoring is the continuous feedback of the information. Both use essentially the same kinds of information, but use them in a different way. And it's important to kind of have that concept in your mind. Okay. So an evoked potential, which is one of the major tools we use, is the electrical response to sensory stimulation, either visual, DEPs, sensation, SEPs, hearing, or to motor stimulation with transcranial motor potentials, or compound muscle potentials. Kind of made this point already, but I want to make it again. The size of these signals are small, so EMGs are on the order of 1,000 microvolts. Transcranial motor potentials can be 100 to 500 microvolts. They can be as much as 1,000 microvolts. Compound muscle potentials the same. Then we start to get down to EEG, visual potentials, SEPs, and brainstems. So you can see the range of the signals that you want to record. You want to record them at the same time, and you want to display them in such a way that these inherent amplitude differences don't create a problem for you. We're not going to talk particularly about visual potentials in this discussion. We've used them. I think I've written 3 or 4 papers on them, but they're very hard to get. Anesthesia is very difficult. Stimulation techniques aren't good, and I thought it wasn't worthwhile to spend time on it. But we will talk about everything else. As we hammered home yesterday, the key to understanding everything in neurophysiology is synaptic physiology. You have the excitatory postsynaptic potentials. They tend to be glutamatergic or cholinergic presynaptic neurons. The neurotransmitter binding open sodium channel, and you get an excitatory postsynaptic potential that moves you away from the resting potential, which is controlled primarily by potassium, up towards the threshold at which the neuron will fire. The inhibitory postsynaptic potentials tend to be GABAergic or glycinergic, and again they open the channels for potassium and chloride, which tends to move you away from the threshold, hyperpolarizing the neuron, decreasing the probability that the neuron's going to fire. I use the word probability a lot because I think of all these things as statistical in nature and stochastic in nature. When you depolarize a neuron with an EPSP, you're increasing the probability that the neuron's going to fire. It doesn't guarantee that it's going to fire. It changes the probability that it's going to fire. When you hyperpolarize the neuron with an IPSP, you're not guaranteeing that the neuron isn't going to fire. You're changing the probability that it's going to fire. So when you think of, the pyramidal neurons we were talking about, with 100,000 synaptic connections onto a single neuron, okay, the likelihood that that neuron's going to fire is the accumulated effect of all of these EPSPs and IPSPs, so that are impinging on that neuron. So it's a stochastic, it's a random process, which you then try to synchronize when you produce an evoked potential. And in the EEG, it's also synchronized, but it's synchronized through natural reverberatory circuits that flow through the thalamus. So all of these things have to be driven in some way, and they're stochastic in their fundamental nature. Spontaneous activity, there's no averaging involved in these. So the electroencephalogram, as we talked about, it's a summation of volume conducted activity produced by EPSPs and IPSPs into a cortical pyramidal cell. So remember the dimension we're talking about. You got a single cell, 100,000 synaptic junctions, and it takes about 50,000 of these cells firing synchronously to produce detectable signal changes at the scalp. So there's a big process going on here. It's not deterministic, it's not unitary. It's this big population of things acting in a way which reinforces each other. The frequencies of the oscillations in the EEG are driven by projected activity from the thalamus. So these reverberating circuits which flow through the thalamus, and if you remember the cortical diagram, the inputs to the pyramidal cells came from the thalamus and they came from the inner neurons. So the inner neurons are modulating this effect which flows in from the thalamus. And even though that, I'm using that description for the EEG, and we'll talk about the EEG in more detail, this is exactly the same idea for evoked potentials. So, and so it drives a lot of what we do in the operating room. The EMG, Again, summated muscle activity, in this case produced by EPSPs on muscle fibers. And the activity is driven by activity in the alpha motor neurons. So you've got this pool of neurons producing afferent outflow, producing excitatory activity in the muscle fibers, and that produces the EMGs that we see. So EPSPs and IPSPs are really, really important. So we want to start to talk about extracting the evoked potentials from the background noise. So you're going to try to record an evoked potential from an ongoing EEG. So to do this, trains of stimuli are applied. Trains of stimuli are applied to evoke stereotypic activity. And I emphasize the word stereotypic activity. The reason these evoked potentials are useful is that if you set things up the same way every time, you're going to get essentially the same response every time in a normal person. And if you test the same person year after year, exactly the same way, you're going to see essentially the same response recorded from the same electrode locations, except for the effects of aging. And I've done that on myself, so I've followed myself for many years, and my stereotypic response didn't change except for the effects you would expect to see with aging, and we'll talk about what those effects are later on. The activity occurring after each stimulus over a fixed period of time, the observation interval, is added to the preceding sets of data. And then taking the average of these extracts, I want to expand on that a little bit, because there's some assumptions there that are important to understand. I'll have a figure which will make this point, but I want to kind of explicitly make clear what the assumptions are, because if those assumptions aren't met, which they may not be, it will distort the results of the data you get, and it could change your interpretation when in fact it's the fact that the assumptions aren't being met. So we're going to talk about unaveraged data to start with. So you apply a stimulus. So this is going to be evoked data, but unaveraged. Then you get something that looks like this. And this is our observation interval. So you remember this morning we said the observation interval was 10 milliseconds long. So this is 10 milliseconds. Okay. You apply another stimulus, and you get something that looks the same, and you apply another stimulus, and you get, and in fact what this evoked activity looks like from the scalp, it looks just like EEG, because the signal you're actually interested in is buried in this ongoing EEG. So to extract that signal, you make several assumptions. On the brainstem potentials, we want to extract this. We're going to do this 1,000 times. Say, we want to extract an auditory brainstem potential, and it's going to look like this. Okay, and this would be wave 5, say. Okay, so when you average these all together, that's the signal you want to pull out. That's the idea of getting a signal out of the noise. So the noise is actually this background EEG activity, which in reality isn't noise, but we call it noise for signal extraction purposes. So to pull this signal out, you have to make several assumptions. One, that the data is what we call stationary. And what that means is that the fundamental statistical properties of the data doesn't change over time. So if I took a sample here, at the same time all the way down through the raw data, and I looked at the statistical distribution of that data, it would have some distribution like this. If I took a sample here and looked at that data at that sample point, it would have a statistical distribution that would be pretty much the same as the statistical distribution here. Okay. So this is a very fundamental idea to this whole process. The other thing that's fundamental is that the distribution of the data is normal or Gaussian. So those two assumptions are what underlies all this extraction of signals. It's kind of, again, important to have that model in your mind, because if for some reason the data is changing rapidly, the fundamental properties of the data is changing rapidly, it can change the value of the average. If the distribution is skewed for some reason, it can change the value. You may not be able to determine, except that you're getting a result that doesn't make sense. That's maybe the only way you can determine it. So what happens is, if you have Gaussianly distributed data and you average it, and we think about this as averaging across the sample points, so each wave shape is made up of digitized data, so you have all these sample points, and you average across 1,000 of them, you end up with the average value here. And the key idea is that the noise in the signal decreases by 1 over the square root of n. So the noise gets smaller as n goes up. Okay, so if n is 100, see this little n in here is 100, square root of that is 10, so the big N would be 1/10 of what it was at the beginning. If this is 1,000, it would be whatever that is, 1/33 the square root of 1,000 would be 1/33 roughly of what. So what you're pulling is you're pulling the signal out by doing this averaging, which is effectively decreasing the noise component by the square root of the number of things that you're averaging. And to do that is dependent on these two assumptions. And that's the key driver in the average evoked potential methodology. There are other kinds of noise that can come into this, not just the intrinsic noise of what we call the intrinsic noise of the EEG, but there can be artifactual noises from cauteries or bipolars or warmers or whatever, which you may not be able to get rid of because of their size, because of their own statistical properties. So there are things you got to do that are different to battle those. But is this clear? It's an important point. So there's evoked activity and there's averaged evoked activity, two different things. So there's activity that we evoke, compound muscle potentials, which we don't average because the signals are so large. What we're trying to get at is so big that it doesn't need to be averaged to appreciate its structure. There's compound action potential, so action potential activity in a neuron other than single unit activity. There are D waves, which are the spinal cord efferent activity produced by transcranial stimulation. And then there's evoked averaged activity, median nerve potentials, ulnar nerve potentials, posterior tibial nerve, perineal nerve, brainstem auditory potentials. Transcranial motor potentials may or may not be averaged. Some people average them. We don't think there's any reason to within visual evoked potential. So, going back to our argument about what produces these things, just to reinforce that, we have our pyramidal neurons. You get a projection from the thalamus, which is excitatory. It sets up positive charge inside the membrane, negative charge outside the membrane, currents flow, producing a positive charge here in the apical region, and this is seen by volume conduction as a positive charge at the scalp, reference to some other recording site, which is represented as a grid. So this concept is key, and we've got to make sure we have that in our minds. So just to reinforce the averaging idea, this is one trace, the assumption the signal at each sample point has a Gaussian distribution and the signals are stationary. These are really the assumptions that drive this thing, so they're strong assumptions. In this particular case, you can see there's several signals being averaged, and you eventually get down to where you've extracted whatever the signal is. What is n in that case? N is 100. So this signal, the noise component of this has been decreased by 1 over the square root of n, which makes the signal 10 times larger compared to the noise. Now, we do another calculation in our system that we play with, which actually, instead of averaging, we take a response, and then the next response we subtract it, and that gives us an estimate of the inherent noise. So you can actually not only compute the averaged response, but you can compute what the inherent noise is within the response. And, that's helpful when you've got a very sick patient and you're trying to decide is what you're following real or not. So again, remember, the decrease in noise is proportional to the square root of the number of stimuli. So this morning we were using 1,000 stimuli, so it's a factor of 33 or so. If you still don't have a good signal, you may go to 2,000, 3,000. We tend to work with fewer stimuli. We normally do brainstem potentials with 500 and median nerves with 32 to 64. But it's a preference thing. So this is kind of a roadmap of where we're going to go in terms of the data and how it's used. So the way to look at this is these are kinds of surgeries down this column, and these are modalities, EEGs, EMGs, upper extremity evoked potentials, lower extremity evoked potentials, auditory brainstem potentials, cranial motor potentials, or compound motor potentials, or D waves. So spine surgery, cervical, you would tend to use EMGs, upper extremity motor sensory potentials, lower extremity sensory potentials, and transcranial motor potentials or compound muscle potentials. Thoracolumbar, same kind of idea, bit lumbosacral, EMGs. You might use upper extremity evoke potentials to protect the brachial plexus for positioning issues. Lower extremity SEPs to protect the spinal cord and nerve roots. You might use D waves. This is for an intramedullary tumor. You might use D waves to protect the spinal cord. Catecline tethered cord, EMGs. Again, upper extremity evoke potentials for positioning issues, and lower extremity evoke potentials. The brain, subtentorial, EEGs, EMGs, so forth, motor potentials. Skull-based cases, we tend to use almost everything. We may use motor potentials also, but you're going to use EEG, EMGs from most of the cranial nerves. Upper extremity responses, lower extremity responses, brainstem potentials, and so forth. Infratentorial, again, you may use everything. Epilepsy, you may use only EEG. Vascular cases, EEG, upper extremity evoke potentials, lower extremity evoke potentials, and motor potentials. Cardiovascular, same kind of idea. EEG, we usually use EEGs and upper extremity motor potentials. In peripheral nerves, we have neuromas in continuity. You may do evoke potentials, and you may do compound action potentials or compound muscle potentials. So this is kind of a roadmap of if you take all the tools we're going to talk about now in terms of data, how they map into the different kinds of operations. And I don't know, Brent, if you have any thoughts about other operations we ought
No, I think that's
to consider.
fair.
So again, just a quick overview of the ideas that there's continuous data which is unevoked in the sense that we're not evoking it, like EEG and continuous EMG, the distinction being against evoked data and then further against evoked average data. So the evoked data don't need to average because it's so large, has such a stereotypic shape that you can identify it clearly without averaging, and yet you'll find people that will average it. So when I say you don't have to average it, it doesn't mean that people don't average it, and there's nothing wrong with that. And then there's the data which you have to average to extract, and those are most of the evoked potential data, so the average evoked potential data. The idea underlying averaging, two key assumptions, stationary and Gaussian distribution. And then roadmap, where we're going to go from here into case land and the data land itself. Okay. Any questions?